Just wanted to finish up this section on ionic compound. These are the non-exceptions. We'll talk about the exceptions today, but I wanted to finish up this section before we did that. So we did examples 4.2, A, B, and C yesterday, right? Yeah, okay. So as much as you've done, hopefully, a little bit of time anyway, but then also try to catch up or follow along with us as we go through these on your own. Go ahead and make a screen, get us going. Okay, so the question asks, or the on your own 4.2 says, give the chemical formula for the following compounds. We're going to walk through each one of them. Okay, spend a little bit of time on it. You need to make sure that you can do these, preferably if you were able to accomplish any of them before we started, during the bell work time. So I want to encourage you to take advantage of the bell work when it's up there, because it's generally significant for you to get an opportunity to try these things, because I want to go over them. Now, even if you don't get them, it's good for you to try and not be able to do it, because you don't know how to do it, and you pay attention better. If you think, oh yeah, it's easy. Well, everything is easy. I don't have to pay attention to anything. And that's like, I don't understand how I got this grade. Well, you came into everything thinking it's easy and you can do it, instead of knowing, hey, it's hard and I can't. And you pay attention differently. So even little things like this, even though, hey, yeah, the answers to this are in your book, you can just flip back and read the answers, but you're cheating yourself. The on your owns are designed for, again, it's the homeschooling text. They're designed so you can try these on your own, try them fully on your own, and then flip back and see how you did compared to the answer. Not so you can walk through it by looking at the answer and then taking step by step by step. That, again, just cheats yourself. And that's more of encouragement to the folks that are doing it at home than it is to you, because that's not the way we run class here. So on your own 4.2, and the first one, what is the chemical formula for the following compound? Beryllium chloride. Let's walk through the process that we're going to use to figure out the formula for beryllium chloride. What are the first pieces of information I need to acknowledge or write down? Sir? They're chemical symbols?
Yes.
Okay, good. I knew you knew it because you were pointing and making the gestures. So write down the chemical symbols of each. And just so we know what they are, beryllium is Be, and chloride is the ide name. So it's the ionic name or the ide name of chlorine. So hopefully you know that beryllium, Be, and chlorine is Cl. And I'll put this on the slide in just a moment. But what do we do next? Now that we know those two elemental symbols, what's our next piece of information that we need to find out? Somebody else. Thanks. Ma'am, in the back. Use hand gestures like he did, and I'll interpret it. No.
Is it valence?
Right, you're going to figure out how many valence electrons, but for right now that we understand the concept of valence, the shortcut for us is we can determine how many valence electrons it has. If it's in columns 1A through 8A, all the A columns, we can determine the valence count by the column that it's in, right? So we're going to locate both beryllium and chlorine on the periodic table, find out where they sit, and if they're in A columns, we know how many valence electrons they have. So beryllium, where is Be on the periodic table? So it's the second column. It's column 2A on the second energy level, right? Yeah. So we know that beryllium has how many valence electrons? 2. Is beryllium a metal or a nonmetal? It's a metal, right? It's way this side of the jagged line. It's a metal. It's a column 2 element with 2 valence electrons that's a metal. Therefore, metal, it wants to do what with the electrons? Gives them away, gets rid of them. Because it's easier to get rid of 2 in this case than it is to pick up 6. So it's a metal, it wants to give away 2 electrons. If it had its way and was able to give away those 2 electrons, what would its net charge then be? What would the charge of the beryllium ion be if it was able to give away both of its valence electrons? Okay. It was neutral, right? And it gave away 2 negatives. Right? 2 electrons. Each electron is a 1 negative charge. It gave away 2 of them. Since it gave away 2 negatives, it is now 2 positive. Okay? It is 2 positive, because it gave away two negatives. Before it gave away the two negatives, it was neutral. The positives and the negatives balanced, the same number. So if beryllium as a metal gives away two electrons, it gets rid of two negatives, it now must be two positive charge. Does everybody get that concept? Okay? It gave away two negatives, therefore becomes positive. And your metals are going to become positive ions, the cations. Metals give away, metals become positive. Beryllium, two positive, because it gave away two electrons. It's 2s1 and 2s2 electrons. Now, chlorine, column 7, 7a, right? How many electrons then in its valence? 7 electrons. It's a nonmetal. Does it want to get or give? It wants to receive. Because it has 7, it's easier to get 1 than it is to give up 7, right? Think of it that way. That works. So it's a nonmetal. It wants to receive, and it can receive how many? Right, it can only receive 1. It has 7. It's going up to 8. It receives 1. So if it was neutral, and it could receive and did receive 1 negative, its net charge would now be, pardon? It had 7 and it was neutral, right? And it gains 1 negative charge. It is now 1 negative. It's 1 negative. It was neutral and it received 1 negative. It now has a net 1 negative charge. The only time it's really confusing is for the metals that are giving away electrons. You got to think kind of in reverse. I gave away 2 negatives, therefore I'm now 2 positive. For the nonmetals, it received 1 negative. It's now 1 negative. Okay? So the metals are giving up, so you got to think the opposite way. It gave up 2 negatives, therefore it's 2 positive. For the nonmetals, it received 1 negative, therefore its charge is 1 negative. Now, what is the formula for beryllium chloride, an ionic compound that's made up of beryllium and chlorine? Do you remember how we figured out what the formula is going to be now? Remember, these things both have charges. And remember, they got their charges because they shifted electrons, right? Chlorine lost and beryllium gained, and that's how these things happen. The electrons displaced. Remember, when we make the compound, the net charge of the entire compound has to be a net neutral, a 0 charge. So, the shortcut we showed you is what? Anybody want to remind us of the shortcut? Boldly remind us of the shortcut rather than timidly remind us of the shortcut? Yes, sir.
Was it drop the exponent down?
Okay, so the way we described it is we're going to drop the sign, rewrite it with the metal first and the nonmetal second in the same order, beryllium chloride, so it's going to be BeCl. And the subscripts are going to be the superscripts are the opposite. In other words, beryllium is now going to have a subscript of 1, but do we write 1? No, 1 is always implied. And chlorine is going to follow, and its subscript is going to be a 2, like that. Now that's our initial. We have to stop if it's ionic and look at it again and go, is that the lowest ratio? I mean, is it the lowest numbers? Is there a greatest common factor that goes into both of them? And with 1 and 2, we're good. There's nothing that these can go into. If it was 2 and 4, it would become 1 and 2, but it's not. Now, what I want to encourage you to do is look at this and say, okay, this molecule has to have a net 0 charge. Let's check it. To do the check, what I do is I write down how many, okay, this beryllium, how many of them do I have? 1. What is its charge? Positive 2. 1 times 2. I drop the positive or negative because in the ionic they're going to be opposite charges. And what we're trying to make sure is we've got balancing positive and negative. So the beryllium provides us with a net 2 positive. The chlorine, I have 2 of them. See? I have 2 of them, and each one has a charge of negative 1. So technically, this would be 2 positive, and that would equal 2 negative. That's not truly equal, but what we're trying to show is that they're opposite charges, but they're the same number. So that's why I show it this way. So the beryllium provides, 1 beryllium ion provides us with 2 positive charge. 2 chlorine ions provide us with 2 times 1 negative each. And the net is, does 1 times 2 equal 2 times 1? Your response is, again, trying to keep the math as low in the elementary grades as possible. Does 1 times 2 equal 2 times 1? It does. We're right. Given that these are opposite charges. They have to be opposite charges. Remember, we can have metal and nonmetal, and later we're going to learn about nonmetal and nonmetal, but we're not going to have metal and metal. Okay? There is no metal-metal compound. There's metal-nonmetal that are ionic, and we're going to have non-metal-nonmetal, which is covalent, which we'll probably get to tomorrow. So any question on how to come up with a formula for beryllium chloride? And I know this is way too hard, right? Anybody? This is way too hard? This is way beyond your ability to do? Anybody agree with that statement? Anybody? Anybody? Nobody's agreeing with me. Okay, good. So by default, you're saying, yeah, this is something we can do. This is reasonable. Let's go on to the next one then, potassium oxide. Potassium oxide. First thing, what are we going to do? Somebody else. What are we going to do, folks? Potassium oxide, need to come up with a formula. Yes, ma'am? Find their symbols on the periodic table, right? So potassium, what is the symbol for potassium? That's one of the ones we had to memorize from page 72, right? Potassium, remember that's not the P. Potassium is K. Good. Oxide is the ide name. We had to memorize those two. Oxide is the ionic name for the element oxygen, and the symbol for oxygen is O. Right. So we look up K and O on the periodic table. What do we find? Where is potassium located? Column 1A, right? Not just 1, it's 1A. Because it's in an A column, its number of valence electrons is the same as the column that it's in. It's in the first A column. So it has how many valence electrons? 1. Is it a metal or a nonmetal? It's a metal. Metals want to give up the electrons and become positive. So when it does what it wants to do, it wants to give up 1 negative, it becomes what charge? 1 positive. Okay. Second half, oxygen. Where is oxygen? Symbol O. Where is it located? 6A. It has how many valence electrons? How do you know? It's in column 6A, right? And it's in column 6A because it has 6 valence electrons. Okay, so it's in column 6A. It has 6 valence electrons. Is it a metal or a nonmetal? So it wants to, what with the electrons? Gain. Wants to gain to 8. How many does it need? When it does that, what charge will it have? 2 negative. Right. Now I just have to go through and do my write it in order and transpose the superscripts as subscripts diagonally. So it's going to be what? Let's try it before we put it up there. What is the formula going to be for potassium oxide? K what? As a group. K? K2O implied 1, right? K2O1, or K2O. Let's check it. When we check it, we're going to say how many ions times its charge. Does that equal how many ions times its charge? In this case, we have 2 with a charge of 1. Does that equal 1 with a charge of 2? Does 2 times 1 equal 1 times 2? Yes. So that proves to us, given that these are opposite charges, but they have equal quantity, that we have created a net neutral molecule. Therefore, for ionic bonding, we're done. We can't add any more, take any more, we're done. That's the only. As a matter of fact, when it comes to combining potassium and oxygen, is there any other way I can combine those two elements to form a compound? Is there any other way? Those two and only those two. Is there any other combinations I can come up with? Short answer is shorter than the wrong answer. The wrong answer is yes. The right answer is no. No, you cannot. That's why we can call it potassium oxide. We don't have to go dipotassium oxide, because it's the only way potassium and oxygen combine to form a molecule. It's the only way they can do it ionically and have a net neutral. And if I had K4O2, I would actually have 2 molecules of potassium oxide. It would be K2O1. All right? Any questions on B? Boom, another one. A little quicker now. Aluminum phosphide. Aluminum symbol, Al. Column, 3, 3A. Valence electrons then are metal or nonmetal? One to give or get? Give, how many? When it does that, what will its charge be? It gives up 3 negative, so it becomes 3 positive. Okay? Phosphide. It's the ionic name for the element phosphorus. Phosphorus, symbol P. Location on the periodic table. Okay, 5A. Valence electrons then. Wants to have 8. How many does it want to receive? 3. When it receives those 3, its charge will be 3 negative. Write the formula, metal first, nonmetal second, transposing and subbing. It would appear to be Al3P3. However, what is the greatest common factor between 3 and 3? 3! So it reduces down to ALP. Okay. Al3P3. Greatest common factor of each is 3. Divide both of 3's by 3 and you get 1. ALP. Let's check it. This formula says I will have 1 ion at plus 3. Does that equal 1 times negative 3? So does 1 times 3 equal 1 times 3? Yes. So we're right. Next one, last one. Magnesium nitride. Magnesium and the ion of nitrogen, right? So magnesium is a column 2A element. It's a metal. It gives up. It goes to plus 2. Nitride is the ionic name of nitrogen. Nitrogen is a column 5 element. It's a nonmetal. It wants to receive. It wants to receive 3 more, and when it does, it becomes a 3 negative. Now, the little different part here is what is the formula? What is the formula for magnesium nitride given this information? Everybody have an answer in their mind? You do? Okay. Everybody? Good. Let's say it together. Ready? The answer is Mg3N2. Right. Everybody had, oh, you got it right. Good thing you didn't say it. Because it might have proved otherwise. Whew. Okay. So Mg3N2. Do you see that? Do you see how we wrote it metal first, nonmetal second, and the subscript is the superscript of the opposite ion. So nitrogen had a 3, therefore magnesium, there's 3 of them. Why does it have to look like that? Because 3 ions of a plus 2 charge gives me plus 6. For our purposes, 6. And then 2 ions, each with a negative 3 charge, is 6. 6 equals 6. It's a net neutral molecule. Magnesium nitride is Mg3N2. Yes?
So for that, you just multiply the subscripts for like magnesium's 3 and then above is 2.
Right. So this tells me I have 3 of at 2 each. 3 at 2. And then over here I have 2 nitrogens, and each one of them has a 3 charge. Right. So technically this would be plus 3 equals negative, or excuse me, plus 6 equals negative 6, but I'm taking that plus and minus away from you because I couldn't write that equals. It's not equal. What I'm saying is we've got to make sure that the amount, the number of positive charges equals the number of negative charges so that it's a net neutral. And if this is a true statement, if the number times the charge is equal to the number times the charge, if that's true, then we're right. Okay, on your own 4.3 asked, what is the chemical formula for the compound that forms when cesium and nitrogen are reacted together? Cesium and nitrogen are reacted. What is the formula, and then what is the name? Walk through this together. All right. Cesium and nitrogen. What is the first thing I have to do? I've got to find the chemical symbols for cesium and nitrogen on the periodic table, don't I? You agree with that? Okay. Where is cesium located?
So just the, we didn't have to
That's carbon. C is carbon.
CE.
Oh, CE?
Yeah.
It's CS. Cesium is CS. And so cesium is located in column 1A. Metal or non-metal? It's a metal. In column 1, it has one valence electron. What does it want to do? Get or give? Give. It's giving 1. When it gives its 1, what will its charge be? 1 positive. Right. The second half was cesium and nitrogen. We've just done one with nitrogen, right? Nitrogen is a column 5A. Metal or non-metal? Non-metal. Non-metal, therefore, it wants to receive or give. Correct. It wants to receive. It has 5. It wants 8. How many does it need to receive? 3. When it receives those 3, what will its charge then be? -3. Okay. Now I combine those two things, right, to come up with a formula. Those pieces of information. What will the formula be for cesium, or not for this molecule? I almost gave you the name. For this molecule that combines cesium and nitrogen. It's ionic, so it can only form one combination. So every time we talk about cesium and nitrogen combining together to form a molecule, it's going to form this molecule. This is the only molecule it can form ionically. What will the formula be? We're going to write the metal first, so it's going to be CS something. What's the something? What's the something on the cesium? Go ahead, be bold. 3. How do you know? No, you're right. You're right. Go with the good. Yeah, it's 3. How did you come up with 3?
I used the superscript of nitrogen.
Correct. She used the superscript of the nitrogen, which was 3, as the subscript to the cesium. And then nitrogen is next, and it has a subscript of 1, but that's implied. We don't write 1s. So there's the formula for the molecule that's made whenever cesium and nitrogen react to form a compound. What is its name?
Magnesium nitride.
Well, that's our balance check. See, we've got 3 at 1 equals 1 at 3, and it checks. And you're right, cesium nitride. Why? Cesium, we use the metal name. It's an ionic formula. It's an ionic compound. Cesium, the metal, gets its full normal name. The nonmetal gets its ide name. The ide name of nitrogen is nitride, so cesium nitride. And if I said cesium nitride and didn't give you the formula, you should be able to then go backtrack it, take cesium nitride, and figure out what the formula would be from that. We have about 11 minutes, right? Okay. Thursdays throw me off big time. So let's look at this one. Handling the exceptions. We are now on page 143. There are exceptions to the ionic compounds. And here's the deal. The exceptions are due to the fact that certain metals have a tendency to form multiple cations, which means there's certain elements that they're not happy with just being in column, they're not as simple as, hey, it's in column 4, therefore, and it's a metal, therefore it wants to give up 4. There's some weirdness that happens in a few of them. If you remember, we gave 3 specific exceptions, and also want you to realize that all those transition metals, all those ones that have d orbitals, and if we look at the periodic table, that whole center section where the d orbitals are at, when you start adding d's into these things, they start acting weird. And anything that's in the transition section is going to fit this model of how we talk about exceptions. So, how do we let you know that you're dealing with something that's exceptional? Notice I said that? Exceptional. It's weird. Okay? Well, the ion is identified by a Roman numeral that designates the ion's positive charge. These are going to be metals. They're going to be forming cations. So they're going to be giving up electrons. The question is, how many do they give up? That's why it's important for you to say, what column is it in? It's in column 2. No, that's not enough information. It's in column 2A, because certain rules. If it's in column 2B, we're going to have to look at it like an exception. And then there are some that are in A columns that are exceptional. Now here's the deal. How do we know If I'm saying it can form different ions, what I'm telling you is it can have different charges. We look at nitrogen. Nitrogen is a column 5A element, and we've said every time it's a nonmetal, therefore wants to receive 3. Nitrogen forms 3 negative ions. That's what it does. But there are elements that you don't know what the net charge of the ion is. You have to be told what it is, because it can form more than one kind. There's only a few of them. Matter of fact, if you were to flip over to page 144, table 4.2, it gives you the most common ones. But you're going to be able to recognize real quickly if something is an exception, because it's going to have the Roman numerals behind it. Notice on the name of the ion on the right, you see chromium 2, chromium 3, iron 2, iron 3, copper 1, copper 2, gold 1, gold 2. Everybody see what I'm talking about? Okay. You have to be able to read Roman numeral, by the way. So how many is this? How many is this? How many is this? Okay, now that's, I'm trying to do 3, but if I did that, it's 4, right? Okay, so to be able to count to 4 in Roman numeral, everybody good with that? I mean, I don't have a slide that says here's 1, here's 2, here's 3, here's 4, but hopefully you can read. It's count the sticks, except for the one that has IV. See, because like my name, I'm a 3rd, my son is a 4th, and so nickname I call him Ivy. See, so we're going to designate when something has a exceptional charge by putting a Roman numeral after it, and that's going to tell you what its charge is. For example, tin rhymes with sin. That's how you remember it's SN is the chemical symbol for tin. But if I tell you that you have an ion of tin 4, right? If I say you have an ion of tin 4, you're like, tin 4? What? Tin 4. It would be written as tin, Roman numeral 4, and that tells you that when it forms its cation, it's formed a +4 or 4+ ion. Okay, now here's the hard application question. Let's suppose instead of tin 4, I have tin 2. What do you think the charge on the tin 2 cation is going to be? Yeah, +2. Okay, that's as hard as it gets. So if you're given an element and you're told, like for example, tin 4, in your mind hopefully you see tin, parentheses, Roman numeral 4. What does that tell you? You're talking about a +4 or 4+ cation of tin. All right? Same thing with tin 2. And that's why table 4.2 goes through. If you notice on the left, like for chromium, for example, it says chromium 2+, chromium 3+. On the far right column, it's chromium 2, chromium 3. Those numbers in parentheses, those Roman numerals in parentheses, are the same as the quantity of the plus charges in that cation. So, what's the chemical formula of tin 4 chloride? Okay, now we're going to actually apply it. Tin 4 chloride, I have tin, right? That's one of my elements that's going to be involved here. Let me ask you, do you need to even figure out what column it's in? You need to know SN is tin, but does it matter what column it's in? No, because you've already been told what? It's going to form a +4 ion. How do you know? There's the 4 right there. Don't worry about where it's at. Why? Because after you take off 2 of the p electrons, then you start messing with the d electrons, and it gets all wonky. Okay? So it's telling you here, you're going to have tin that has a +4, 4+ cation charge. They gave it to you right there. The only part you've got to do now is go, okay, what about this thing? Well, chloride is the name of chlorine. Chlorine is a column 7A element. Chlorine is a nonmetal. It wants to get. It wants to get to 8. It has 7. It wants to get 1. When it gets that 1, it's going to have a 1 negative charge. What now is the formula for tin 4 chloride? Anybody? What is the formula for tin 4 chloride? Sir?
SN1CO4.
Yep. That is the molecular formula for tin 4 chloride. And we're going to check it, I think. Yep. We have 1 ion with a +4 charge. Does that equal 4 ions with a -1 charge? Yes, it does. It's a balanced, it's a net neutral molecule. Okay, so is SnCl4, here's where it gets weird too then. What's the chemical formula for the tin 2 chloride? We do the same thing, right? Tin, sin, Roman numeral 2 means what? It's going to form a cation with what kind of a charge? 2 plus. Well, the other one had 4 plus. Yeah, but it's a different thing. This is a tin 2. That was a tin 4. See that? Now, the second half is exactly the same. Chlorine is still column 7A, nonmetal, wants to receive. When it does, it receives 1. Boom, there's my... Now what's the formula for tin 2 chloride? Tin SnCl2. See? That's how we handle the exceptions. They will tell you, using a Roman numeral, what amount of positive charge the cation has by giving you that Roman numeral. Okay? We have questions on that? We're going to take the next 3 minutes, maximize it by doing what's the name, this is example 4.3, what's the name of the ionic compound CuCl2? Now, this is where you go and say, Cu, what's that? If we don't know the name yet, but wait a minute, wouldn't it just simply be, this is a metal and a non-metal, wouldn't it just simply be copper chloride? This is where you got to stop and go, wait a minute, that sounds like a trick question to me. Because I know that's a metal and a non-metal. It's not copper dichloride, right? Must be there looking for more information, which means I probably have an exception here. Right? So I'm going to look up copper in the periodic table, and I'm going to find out that copper is in column 1B. Boom, guess what? We have an exception. So what's its charge going to be? I really don't know yet. I don't know. So I'm going to put a question mark. Copper, something positive. Is it a metal? Yes. So I know it's going to form a cation. I know it's going to be a positively charged ion. I just don't know how much positive it's going to be. But I do know that chlorine is a -1, right? Column 7, A, non-metal, wants to receive, has 7, goes to 8. When it does, it's 1 negative. Now, I know what? I know, let me check my, I don't want to reveal too much here, that I was told that it's copper chloride, or copper, and 1 copper and 2 chlorines, right? Well, let me do the math. I haven't taught this in years past, but this is why I've set you up with this. Because look at 1 copper times what's its charge? I don't know. Equals 2 chlorines, each with a charge of 1. 1 times something equals 2 times 1. What is the something? Okay, good. It's a 2. What does that mean? That means we're looking at copper 2 chloride. Why? Because the copper has to have a +2 charge. Therefore, I don't need to know all the options, but I do know that this copper is forming a +2 cation. It's a copper 2 chloride molecule.